In summary, if you want to solve an inverse problem involve AX equal to B, where you want to solve the unknown X, if the system matrix A is a special matrix, such as the band matrix or the tri-diagonal matrix, then we can use a more efficient algorithm such as the Gauss Seidel and the Thomas method to solve this problem instead of using the Gauss elimination and LU decomposition method. You must know how to differentiate between the band matrix and also the tri-diagonal matrix. So for these two examples, both of them are band matrix. This is because this matrix has non-zero at the diagonal components here, as well as this matrix. Therefore, both of them are band matrix. So for band matrix, we recommend to use the Gauss Seidel to solve it, as the Gauss Seidel method is more efficient compared to the Gauss elimination as well as the LU decomposition. If you have band matrix with bandwidth equal to 3 in this case, we call it as the tri-diagonal matrix. And for the tri-diagonal case, we do not use the Gauss Seidel or the Gaussian elimination and the LU. We are using the Thomas algorithm to solve it. This is because Thomas algorithm can solve the inverse problem faster compared to the other methods in this case. So bear in your mind, if you solve the inverse problem that involves band matrix, go for the Gauss Seidel method. And if you solve the inverse method that involves the tri-diagonal matrix, then you go for Thomas method. In general, these are the steps that you use to perform the Gauss Seidel method in order to solve the inverse problem. In this case, you have AX equal to B and you are going to find what is the unknown X. And the dimension for A matrix is n times n in general, and X matrix is x1 to xn, and your B matrix is from B1 to Bn. In the first step, the iteration is 0, means that before the iteration starts, you need to express the xi at left hand side. So your I from here is equal to from 1, 2, 3 until n. From the matrix, in the first row, you can obtain the x1 in the function of x2, x3, and so on until xn. You continue with the second row or the second equation here to find the x2 in the function of x1. So x2 is not included here because x2 is on your left hand side. So you continue with the x3, x4, and so on until xn. From the third equation here, then you can express x3 on the left hand side and put the other x at your right hand side. And this x might include x1, x2, x4, and so on until xn. If you have n equation here, then you continue to solve this and obtain the xn on your left hand side. And then we assume all the x is 0, therefore x1 until xn is 0. In step 2, the iteration is equal to 1, means the iteration starts. Then you need to calculate the xi from I equal to 1 until n. You need to put the assumption x1 until xn inside this function here. So after you include on the right hand side, you can compute the x1 until xn on your left hand side. So this is the new x that you obtain in the step 2. Step 3 is optional, means that you can choose to apply this equation or not. If let's say you don't want to apply this, you can continue with the next iteration and so on until meet the stopping criteria. However, in some problems, it might take a long iteration to meet the stopping criteria. For example, it takes 1000 iterations, only it stops. In this case, we may consider to apply the step 3, which is the over-realization, in order to fasten the convergence rate. To achieve this, you need to choose a suitable lambda within 1 to 2. Let's choose the lambda to be 2, and then we substitute it 2 here. 1 minus 2, you obtain negative 1. XO is the solution that you obtained from the previous iteration, and X new is the solution that you obtained in the current iteration. In the previous iteration, we have iteration equal to 0. You obtain the solution XO, which is equal to 0. Then we can substitute inside this answer, and then you continue with the current iteration at 1, and you obtain the xi from here. So we can substitute this inside this equation as well. Then you get the new x from the over-realization result. In the step 4, we will continue with the iteration equal to 2 that involve the step 2 and step 3, and continue with iteration equal to 3 and so on until we meet the stopping criteria. Once the iteration stops, you obtain the solution here, and you can substitute inside this equation and check the left hand side. If the left hand side equal to the right hand side, then we can say the solution obtained from the Gauss Seidel method is correct. These are the general steps when we perform the Thomas method to solve the inverse problem. Don't forget we apply the Thomas method on the tridiagonal matrix only, where you have the bandwidth equal to 3 elements here. In step 1, Thomas method perform the decomposition similar to the LU decomposition, but in a better efficiency. This is because we perform the forward elimination only at this region. For example, if you want to find your lower and upper matrix, so your lower matrix must have 1 at the diagonal. So imagine that you have 3 times 3 matrix here, then your lower matrix should have 3 times 3 matrix also, as well as the upper matrix. So for your upper matrix, the component A12, A33 here should be remain the same. Let's perform the forward elimination to the A matrix here. So we will start from the first row. So since the first row is your pivoting equation, then A11 and A12 will be remain the same. Therefore, A11 is appear here. Then we can continue with the second row here. So to make A21 equal to 0, we need the factor A21 divided by A11. By taking this equation, row 2 minus row 1 multiplied with the factor here, then we can take A22 minus with row 1 A12 multiplied with this factor. You can change the A22 here become A22 prime. So A23 remain. Therefore, you obtain your upper matrix here to be A22 prime. So A22 prime is the forward elimination result by using this equation. Next, we continue the forward elimination at third row, and you want to make A32 here equal to 0. You need the factor A32 divided by this component, and you need to be careful, this component has changed to the A22 prime. In the previous forward elimination, therefore the factor is equal to A32 divided by A22 prime. By using this equation, row 3 minus row 2 multiplied with this factor, then you should change A32 equal to 0 now. We continue with the A33. After the forward elimination, you obtain A33 prime. With that, this is the result for the forward elimination, which is equal to your upper matrix. With that, you success to find the lower and upper matrix by using the decomposition of the Thomas method. So this method is faster and more efficient compared to the LU decomposition. Because we need to perform the forward elimination at very few elements only here, and also we do not need to store the 0 outside the diagonal elements here. Therefore, we can use less memory and the computation can be more efficient. Once you get the L and U matrix, then we can continue with the forward and backward substitution by using this equation. So we can substitute L inside and your B vector inside this formula. You need to find the D from the first row, continue with second row and third row. Then you can find your D1, D2, D3 corresponding. Once you get the D vector, you can substitute inside this formula and substitute the U matrix inside this formula. Then you can find the X starting from the last row to find your X3, second row to find your X2, and first row to obtain the X1. So this is the solution, and to check the accuracy, you can substitute back to the AX equal to B here. Check the left hand side. If left hand side is equal to the right hand side answer here, then we can say that the solution obtained by the Thomas method is accurate.